approach the dynamo problem of the interstellar medium. And this means that we have to study the dynamics of supernova explosion and see how a dynamo process can be generated. In order to do this, different work that we are also doing, we are studying turbulent diffusion. We have some Germans and other people, but I'm not going to speak about this today. I'm going to speak about these different ingredients that we put in our simulations, and I will show the results we obtain. The supernova explosions, the aspect of supernova explosion that which we are interested are the mean square velocity, about 10 kilometers per second, and the correlation lengths up to 100 parsecs. This is of course correlated to the fact that supernova explosions go through different states in the explosion. And going toward the simulations, we put rotational flow in simulations, and in which in this kind of flows we see that we should assume isothermality. We can have electricity generation only through viscosity, and we will see how this term works in the equation. And there is also the question: can vorticity be generated by dynamo action? At the moment we say no. This will up to this resolution, as is shown in the work by Tony and Axel in 2006. So for the time being, no dynamo generation of vorticity. Why dynamo generation? Because the equation of the governed vorticity is pretty similar to the equation that governs magnetic
useless.
induction.
Mirror symmetry, yeah? Why is that? I don't know, that's what the inputs get is coming.
This is a simulation that we've done, but this is taken.
I mean, I assume I can post-process, flip it somewhere.
What we are doing, we are generating this explosions, actually this spherical flow, through this kind of forcing. And so we are localizing expansion waves. Of course, the starting point for simulating supernova explosion. Of course, we are doing this with TensorFlow. And we see
the boxes are showing the density?
yes, we are. Yeah, actually, we see here that this is the expansion, and then at some time, more or less, everything starts to be turbulent. So just this is just the density because it's just dynamic, so it's just an expansion wave.
So I don't know if it's true, but I heard this argument that the dissipation timescale in the ISM for turbulence is smaller than the characteristic times for supernova explosion. So a supernova explosion cannot be the only driver of ISM.
The energy input is certainly more than sufficient. It's 100 times more than what is required for driving the turbulence. And of course,
the argument is not that it wasn't time. The argument was that the turbulence of the drives get dissipated over length and time scale, which are much smaller than the characteristic correlation length and correlation time scale of supernova in the ISM. So that basically you haven't explode a supernova, you inject turbulence, but the turbulence decay faster.
But who's saying
than before the next one. But before the next supernova explosion.
So, basically, you think that it doesn't make sense for two explosions to study the collision between.
No, that's I don't know, but I heard this argument. That basically, you get an explosion, you produce turbulence decays, then you have another explosion, you produce turbulence.
Yeah, but I mean, we have now a lot of simulations. First ones perhaps really by Marit Coppi and the rest of us. And there were previously, before that, simulations by other groups in 2 dimensions, in Vasquez and Marini, for example. And nowadays, DelSordo, of course, is doing such simulations, and there's, and of course, this other guy in Daviles in Spain, or Portugal rather. So they show nothing consistent with saying that it's decaying. So that's now over the last 10 years.
More or less, the most question on rating in practice is
So it's 130 50. And what is the dissipation length?
Dissipation.
Yeah. You inject the turbulence locally on the supernova sites, and then the turbulence.
But the dissipation lengths can be as small as it wants. The main thing is that you can sustain the epsilon, the energy dissipation, the energy rate.
If I inject turbulence in one point,
Yeah.
Turbulence then will spread out,
Yeah.
and it will decay, as it does. So
Yes.
So the
But
question
it goes
is
to smaller and smaller length scales.
Yes, because all
Down the cascade.
smaller and smaller length scale, and so it will. I mean, if there is a supernova on a galaxy every 50 years, and a supernova will drive turbulence over something like 1 parsec or 2 parsec scale in that period, then if you take the volume of the galaxy and you divide by how many cells you have, the math on top of my head, then you can say how many years will pass between one supernova and the next exploding in the same volume.
Yeah, so
And
I'll show you later a simulation of ours.
what has to be investigated is different length on this scale.
no, that was just a question.
Yeah, so basically the difference in simulation will be either not put two expansion waves at the same box.
But also for the supernova type 2, you're going to be a condensed, you're able to form several supernova in small, relatively small distance.
Yes, but you have, I think there's an observation that shows that the level of turbulence in galaxy does not show any correlation with star formation. So if you do, I guess, parallelization measure of the coherence length, it does not change a lot if you move from star formation region to parallelization.
Yeah, the delay time is just a little bit too long for that. The delay time, which is the lifetime of the star, of course,
Yeah.
is just a little bit too long for that to be a significant pattern for correlation, I would think.
Anyway, and this is the equation of the evolution in time of vorticity, and we see that there is a time with kinematic viscosity. So it means that in principle, even if you don't have vorticity at the beginning, through viscosity we could observe generation of vorticity. But as I showed here, show here two things. First, that the vorticity that are obtained in work only with viscosity, with that kind of viscosity, very low, very small. And second, that is it is pure vorticity. You see here, for example, let's have different values of vorticity for two different resolutions that you put in the box. So likely this vorticity is being confused. The real vorticity and the pure vorticity that is both present because of the resolution. So when we go back to this equation, actually this term not at the moment is not considered to be important. And yes, I show this picture because just to show the difference we put in our equations, so that are rotation and that are shear, and then there is also volatility that we can find. That we simply speak the isothermal condition for the And there is also the effect of stratification but we are not considering it in our simulation. And so here I go to this equation. This the previous one plus the time due to the rotation. And in this plot we have our results. So the vorticity versus the relative number. And here we show different simulation we performed. Most important is this one, which we have finite correlation time in our forcing, not so big Reynolds number. And we have said here in this range of numbers, more or less linear correlation between vorticity and correlative number. While when we go to more correlative number, we run some simulation for different forcing, from finite forcing time and to delta correlation, intercorrelated forcing time. And we see that for different Reynolds number we obtain different values of vorticity. And most important, all these values are not going to zero. That's the value that should be expected when correlative number is zero. So that is the case which we interpretation. So likely here we have some spurious vorticity in this region. But let's say we observe this in some correlative number linear growth of vorticity. And we remove rotation and we have shear. And shear, yes, I show simple plot. And that's same more or less. For more shear number, we don't go to zero. So it should be some curious statistic. But in some range, you observe kind of linear growth. Anyway, I will actually in the real interstellar medium, this phenomenon not the most important. At least not as important as barometric term that we have here in our equation after moving shear and without shear and without rotation. So we have viscous heating, it means the continuous increase of temperature. So that means that some field changed and what is called study system in steady state. And so we have a cooling term in our simulation. And this is what we obtain. So this is a 2D simulation. And so what we have here, we have the first explosion, so periodic box, so only one explosion at the beginning, and we see here the barometric term is only some fluctuation. We don't have the barometric term, and the same for vorticity. While when we add the second explosion, that is happening here, at the beginning we start with a barometric term and some vorticity. And then when the situation becomes more stable, so that vorticity is increasing, but what we observe that is correlated with what we say. We observe that the vorticity is mainly produced in the region in which these two point shocks in concrete. So I didn't say that we are running for a weak supersonic condition. So it means that there is a weak shock taking place here, and we see that in correspondence of these two fronts here, we have the biggest production of vorticity. Also for this experiment, it's important to check what we say. And these are also the results. Here we got the value of vorticity versus the barometer. We got the angle between these two gradients, the response for the barometric effect. And we see that it's more or less constant, it's changing, but not changing too much. And yes, it's Reynolds number and Mach number. So this means that, of course, here we are running the simulations until the situation time. So here is part of the block inner block. Of course, in this case, with Mach number. And in this case, we can say that we have 7 net production of vorticity. This brings me to my conclusion. Vorticity production is a diffuse with shear rotational therapy. But only if we have this, we consider this value, as I showed you in the previous plot. Otherwise, we have spurious vorticity. But what happens in galaxies? It happens with Breuil number and also shear number of this order of magnitude. So this tells us that barometric is much more important in shear rotation, generating vorticity. And mean vorticity, simulation is a product of the symmetry of offshocks. And just a reference for the table is
Yeah, thanks. Questions? Yes.
What do you call vorticity production? Volume integrated or root vorticity?
not large scale.
And why it is important?
Why it's important? Because actually this is important for a small scale what we are referring for a small scale dynamic production. But of course the problem with galactic dynamos is also on a large scale. But this is
small scale.
yeah, of course. I mean, there are two different problems, of course. Galaxies, so large scale magnetic field, let's say, is important, but with this we try to address toward the better understanding of the small scale dynamic production.
So more vorticity is good for small scale dynamics.
Other questions? Maybe one should point out the only reason to get, of course, the paraclinic term is through the action of viscosity. Because if you didn't have any viscosity, you shouldn't generate any entropy. If you don't generate any entropy and you start off with uniform entropy, there would never be a paraclinic term. And then if you compare this with what is in the literature, we have, there was this paper which we were pointed out to by Federer, who was talking about his simulations with a flash code, and he was simulating the isothermal equation, and he was saying he also gets a lot of vorticity generation. And then if one asks why is that, or if one even looks at the equations, he had the isothermal equation of state, and it's completely clear there should be no vorticity generation in that case, absolutely nothing. And he was not worried about this, and we asked him in detail, and he said, yeah, that's because, and so we told him that is, of course, spurious. And he said it's not spurious because it's, there's in the flash code, there's built in an implicit subgrid scale model. Implicit. That's what he called it. And then I asked Bob Rosner, who was at this meeting in Catania, who was, of course, the initiator of the flash code. And he said, yeah, but that's just because there's in the flash code, by default, one uses the operator split. So one uses first the x direction, then the y direction, then the z direction, and then one changes these directions. And by that way, you can, the effective diffusion tensor by no means symmetric anymore. And then it's clear that you're generating, I mean, whatever you would like to call it. If you like to call it some physics, then of course maybe that's not even so wrong, but it's at least not very satisfactory if you don't really have this under control.
But this is only for very special cases that entropy disturbances are related to this question.
Yes, yes.
There is an entropy
Yes,
gradient.
you could say so. Yeah, it was in that sense particularly academic. I personally was still always worried because I mean, as Fabio said, the vorticity generation in the isothermal case is really just due to the dissipation operator. And if that is not correct, you can produce artificial amounts of vorticity, which you shouldn't. But the baroclinic term, you would naively think, has a similar nature, perhaps. Because, again, entropy production has to do with viscosity. It's slightly different, though, because you multiply vorticity, viscosity, which you think is small, with a strain tensor squared. So it's like multiplying by a delta function squared. And so that's, of course, not going to vanish in reality. So now these simulations show quite clearly that the baroclinic term is really the main way of producing vorticity, but only when you have Mach numbers on the order of unity and above, not otherwise.
And there is a stratification, the production should be larger.
This we don't know, because if you take the curl, because on the right-hand side of the velocity equation, you just have g, right?
Yes.
So now you ask what happens when you add g on the right-hand side. You take the curl of g, and you get 0. So it's not obvious that it should be stronger in that case. I'm presenting this in this rather drastic way, but I don't think it's not obvious that stratification makes it stronger, because the curl of g is 0.
The main vorticity production is in the proximity of shocks, because that's where the velocity gradient is the strongest, and that's where you dissipate the most.
But of course, it's only, I mean, the baroclinic term only happens, of course, when they are clean. I mean, there's an angle. What is clean? It's a Greek word. What?
Oblique shock.
Yeah. What is it? Yeah. But what is the Greek word? There's a Greek or Latin word. Is this Italian, maybe? It's Greek, yes. Good. Any other question? So we have time for more. So we have the other paper by Druba, who can tell us in the next minute. Oh, but by the time he is setting it up, I can show the...
No, wait a moment, because we have to...
So I have to change the mode.
Yeah.
Because otherwise I don't have it. Just a second.